Hi everyone. For today's class, we'll talk like the most awaited topic for this for this course, linear regression and correlation. Most awaited because we've been referring to this in the previous lessons, linear regression and correlation. When we talk about the thing about modeling, right? Which we use for like prediction, right? That's why, I mentioned it, like linear regression and correlation. That's why it's the most awaited topic. Okay, so linear regression is part of inferential statistics. No, correlation still part of the descriptive statistics. No, so last lesson, right? Or the last two lessons, right? The last two lessons, statistical computations part 1, part 2. We focus more on the descriptive, right? Descriptive statistics. Now, so for this lesson, it's like divided into two. Correlation, which has to do with descriptive statistics, and then linear regression, which has to do with inferential statistics. But they're very related to each other, very related. In the next lesson, just inferential statistics, but related in a way, related to regression, but not linear anymore. Okay, class, so so in a way, this is divided into two major topics for today's lesson. So we start with correlation, that's part 1, and then part 2, linear regression. But during the discussion of this topic, correlation, I will mention, there are times that I will mention topics in linear regression. Okay, so that's how they are connected to each other. Okay, because we will use correlation in part 2. Okay, class? Okay, class, let's take a deep dive into the first part of this lesson, which is the correlation. So what is correlation? It's a technique used to measure the likelihood of two behaviors relating to each other, or two variables. So relating, when you say relating, we're not talking of cause and effect. So we're not thinking like the x is the cause of y, or the y is the cause of x, or y is the effect, something like that. And x is the cause. We're not talking of that. We're just talking of the relationship between the two behaviors or two variables. And we can describe it, this correlation, using a single number called a coefficient of correlation. Okay, a coefficient of correlation, according to Guilford, is a single number that tells us to what extent two things are related. So again, the word related is there. To what extent variation in one go with variations in the other. Okay, so so it's a single number. I will discuss more about this later. There's a name for this single number, aside from coefficient of correlation, like the person's name associated to this coefficient of correlation. Okay, and not only number that we will use to describe the correlation of your data, but also graph. We can use a graph to describe your correlation, the correlation of your data. Okay, class, but this one is kind of general. Here we'll talk of this type of correlation, which is linear correlation, because there are other like types or kinds of correlation, like quadratic correlation or multiple correlation. But here we're talking only of linear correlation. Okay, and that linear correlation is associated to this coefficient of correlation. So somehow the correlation that we'll talk about here is the strength of linear relationship, because we mentioned relationship, right? Strength of linear relationship between the two variables. Okay, wherein these two variables, we don't care which one is x, which one is y. So we're not talking here of independent, no? In this part, it doesn't matter, no? But it doesn't matter also if you want to associate one variable to independent and the other variable. It doesn't matter also. But in part 2, it matters. Which one is your dependent, which one is your independent, because it has to do with the prediction of your data in part 2. This one, just describing your data. Okay, so we're not really predicting anything here in part 1. We're just describing our data based on correlation. Okay, so as I mentioned, we can describe the correlation of your data in terms of the single number, which we'll discuss in detail later, but also graphically. And it's related to this next slide. about the types of correlation. So when you talk of types here, the types of linear correlation, such as positive, negative correlation, no correlation. So since linear correlation, so we're associating it to a line. For example, if it's positive correlation, you're associating it to a line which rises from, okay, something like this, no? From left to right, something like that, no? That's kind left to right. Meaning, remember in high school, now we know that if you have this line rising from left to right, it has a positive slope. Positive slope, no? When you say negative correlation, it's kind of associated to this line, no? As you go from left to right, it falls, no? It falls. So you know that the slope of this is negative, no? Negative slope. Okay. And then no correlation, actually, not exactly, you know, actually even this two, not really exactly, because when you talk of correlation, it has to do with the points, right? The points. Okay, so when it comes to no correlation, okay, we can just think of the horizontal line. The horizontal line, that one we know the slope is 0, right? 0. Okay. And you know that if it's vertical line, the slope is undefined. But of course, these two are not really kind of very related to correlation. But these two, yes. No? This one with the positive and this one with the negative. You'll find out later why. So I just mentioned this so that you know, when it's no correlation, it's kind of close to 0. Because later I'll show you the single number, right? The single number related to the coefficient of correlation. So graphically, class, we show this types of correlation in a scatter plot. No? Scatter plot. The scatter plot explains the correlation between the two attributes or variables. Okay, so the correlation of your data, we don't graph using a line, no? Okay, we just associate it, no? But really, the graph of your data, if you want to describe the correlation, scatter plot. That's the name of the graph, scatter plot. Okay, so meaning you have these points, no? These points x, y. Okay, on that plane. Okay, but again, don't be misled, no? Because when we talk of plane, Cartesian plane, we're referring to the x and y, where x is the independent and the y is the dependent. But again, in this context of part 1, correlation, it doesn't really matter. But it doesn't really matter also if you put it on a Cartesian plane. If you associate x to to your if you associate the x to be the independent and the y to be the dependent. So, but again, in part 2, it matters. Okay, so let's go into the graph of each. Okay, the graph of each. If you have a positive correlation, how does the scatter plot look like? Okay, how does the scatter look like? Scatter plot look like if you have negative correlation and no correlation at all? How come we can associate it to this line? Especially this two, no? But this one is kind of far, right? Okay, you'll find out here. Okay, let's go to the next slide. Okay, this one. So you notice the, never mind the lines first. Never mind the lines, just the scatter plot. So without the lines, that's the scatter plot, no? If you don't remove the line. Okay, so when you talk of positive correlation, we can describe it in 3 ways. We can talk of strong positive correlation, moderate, this is the moderate, and the weak. Okay. Similarly for negative, now we have the strong, the moderate, and the weak. And this one is the no correlation. So I think now you can know why we associate line, right? Because if you notice, it's strong if the points near the line, this line, right? If it's weak, if these points are what? Far, kind of far from the line. No? But the moderate, neither near, neither far. Similarly for negative. No? The only difference between the two has to do with the direction of the line. Okay. For this one, indeed, it has positive slope. No? Rises from left to right. No? For the negative correlation, negative slope. That's why we can associate. Okay. But when you talk really of scatter plot, you don't put the line there, no? You don't put it here. It's just for discussion purposes. Oh, that's why we put here. And to relate it to part 2, as I mentioned, even though I'm in part 1, I'll mention something in part 2, because this line is the one we're going to find in part 2. And we know that this is it's a graph of a linear function. Okay, linear function defined by this equation. What is that equation that you learned in high school? Y is equal to mx plus b, right? Where m is the slope, b is the y-intercept, and that's what we will find in part 2. And that's the model that we're talking about now, that I mentioned to you in the previous lessons, no? That we will find a model to predict for prediction, and this is the model that we're talking to in the form of equation. Okay, so we will predict the values of y given the x. We will predict the values of so in that context, now part 2, we will predict the values of the dependent variable based on the independent. But in this context of part 1, we don't really, doesn't really matter now which one is your x and y. But if you will use this in part 2, better in part 1, you already established which one is your x, which one is your y. Especially if you connect it to the question of your research. No? Remember, everything that we're discussing now, it's in the context of that steps of scientific method, right? You have a question, you have the hypothesis, and then the methodology, gathering data, collecting data. But here, the lesson that we're doing now is just like in the previous lessons. They're like part of more of the presentation or the analysis of your data. So this will help you in your analysis of your data or the presentation of your data. You can present it in terms of the scatter plot, which will help you in the analysis later. Okay, not only the scatter plot, as well as the one we will talk now, which is the coefficient of correlation. But before I go there, look at this. No correlation. Notice there's no line. That's why I'm hesitant to mention this to you, this one, because we cannot really draw this this line here, no. But this one is closer to the value that we will talk about, no. This one, because the slope of this is 0. Okay, and also this one, the slope of this is positive. So it's also related to that value that we will talk about on the next slide. This one, the slope is negative. So again, this is related to that value that we will talk about on the next slide. Okay, but for the graph, these two only. No, this one is not, because you can't really see this line. No? Can you see that line here? No. You can't really see it here. No? Unlike the other lines, no? The one with the positive slope, the negative slope, you can see. Okay, so no correlation because there really you cannot fit any line here. Okay, but how about the value? So we can describe correlation not only in terms of graph, but also by a single number, na? And it's connected to this person correlation coefficient. Okay, it's a single number which we can obtain using this formula or this. But actually, in our examples, we'll use this. It's more convenient to use this than this one now, because this one has you have to compute for the mean. Remember this notation in the previous lesson. This is the mean, sample mean, no? Sample mean, because the population mean is what? Mu, right? So anyway, in statistics, the person correlation coefficient, also referred to as the person's R, this one. Sometimes it's denoted as capital R, no? Capital R. Which it doesn't matter now whether it's capitalized or small. The person product moment correlation coefficient, or the bivariate correlation. Bivariate because you're considering two variables, no, x and y. Because there's what you call multivariate, meaning more than two. Okay. In the class, there's a lesson about, which we will not tackle, but kind of related to the next lesson. No? Kind of related, but we will not tackle the because this one is linear regression. No? It's also called simple regression. There's what you call multiple regression, which we will not tackle in detail, but somehow related to the next lesson, no? Or yeah, something like that. Okay, so that it's kind of related to the multi-correlation also. Meaning to say, you're considering not only two variables, the relationship between two variables, but more than two variables. That's why multi-correlation. Okay, so and then there you will talk of multivariate correlation. So this one is a statistic that measures linear correlation between two variables no? X and Y. It is a value between positive 1. Actually, it is a value between -1 to +1. Okay, it's because somehow it has to do with the slope, no? Negative slope, positive slope. Okay, statistic. Remember, you know this word, right? Statistics. So it's not the statistics subject. No? Yeah, this one is related to statistics, the capital S. Statistics. This is statistic here has to do with the descriptive measure of the sample. Remember what we discussed in the previous lesson about sample mean, sample median. So those are statistic. Descriptive measure of a sample. We refer it to as statistic, sample standard deviation, as long as standard measure of a sample. Okay, but if you're talking of measure of population, descriptive measure of population, we refer it to parameter. Parameter, no, that's like the terminology, no, parameter. So here, class, you notice the symbol used here is an English alphabet, no, letter from the English alphabet, because we mentioned last time, right? If we're referring to statistic, we use letters from the English alphabet, but if we're referring to parameter, we use the Greek letters. No, like for example, the mean, this one, right? X bar or Y bar. The sample mean, the population mean, mu. Remember, we denote it as mu. Remember this symbol in the previous lesson, right? And then S, sample standard deviation. But if it is population standard deviation, we denote it as this, right? Sigma, Greek letter. Okay, so for the population correlation coefficient, we use this symbol. For the sample, we use this. In other words, if your data set is a sample, use this formula, no? Not the, because sometimes they may be different, no? Remember in our discussion of standard deviation, there's like a difference between the formula of the sample standard deviation and the population. For the population, we use the capital N, but for the sample standard deviation, small n minus 1. Remember the formula there. There's kind of difference, no? That there are times the same, except the symbols, no? But numerically, you will get the same answer, something like that. Okay, that's why just be aware, you know, do you have sample or population? Because possible that your data is population. But since sometimes the issue there is the budget or the time, that's why you get a sample from the population. Okay. So if it's population, if it's sample, use this formula to get your coefficient of correlation or the person correlation coefficient. No? And if you want to know the formula for the row, this is the row, which is also correlation coefficient referring to the population. Explore on this one. I'll just leave this part to you for your research. Now, if your research has to do with population data set, not sample, then look for the formula of this. Okay, for our examples, we'll use this. Okay, so now you'll get a single number here, right? Single number. So using the single number, we can describe the correlation of our data based on this number. Okay, based on this table. No? So if you get 0.9 to 1, we say that it has a very high positive correlation, your data. If you get this 0.9 to 1, 0.7 to 0.90 high positive correlation, 0.5 to 0.7 moderate positive correlation, 0.3 to 0.5 low positive correlation, 0 to 0.3 negligible correlation. Now, you notice the overlapping. Remember, we mentioned this in our group frequency distribution table that if there's like overlapping, the meaning of this is less than. So meaning, if you get 0.90 for R, it's here, no? It means very high, not high. Because this one means less than. So the 0.89 here. The 0.70 here, not here. The 0.69 here. So if it's 0.69, moderate, okay? So that's the way to interpret this. No? They're not really overlapping. No? There's like this understanding already that this one means less than. But sometimes it's really mentioned here, no, under or less than. Remember, I mentioned that in that lesson about distribution table, frequency distribution table. Okay. So now, similarly for the negative now, but of course there's something wrong with the order. No? -1 to -0.9, very high negative. Negative 0.9 to negative 0.7, that's high negative correlation, and so on and so forth. Okay, class, that's based on the number, single number. You can describe your data based on this. Now, how do you correspond the two? You can have correspondence between the graphical and the tabular, no? But before I mention that, class, you notice the negligible, no? That's why I mentioned here the zero slope, no? But really, graphically, we cannot see this, right? Unlike this two. But this one, we can see this, the zero slope, in the table. That's why I mentioned this, no? Because of that zero to the negligible correlation. If you get zero, no? Zero, kind of related to that line, the horizontal line, zero slope. Okay, but graphically, we cannot see that. Now let's correspond the two. Let's have a correspondence between the two. So graphical, if you say strong positive correlation, so because if you have your data, you can get the scatter plot, right? And also the R, right? You can do that. So so as much as possible, when you write the interpretation of your data in terms of correlation, they should match, no? Matching, no? For example, graphically in your scatter plot, you say strong positive correlation. Then numerically, you can correspond this to, if you get like 0.7 to 0.7 to 1, you can say that, no? Strong. You can say strong positive correlation graphically. But of course, numerically, there's a distinction, no? If you get something like this, you will say high positive correlation, and then if you get something like this, you get very high. But how about the graph? If you get this, you can just say the graph is strong also. Strong. Okay, so avoid the mismatch, no? Because you might mention moderate, no? But numerically, it's really it falls between on this. But actually, the moderate is this. Okay, so you understood what I mean, right? In your research, in your future research, be sure that they match, no, the numerical and the graphical interpretation. This is the matching that you can do. So now numerically, if you get R equal to this 0.5 to 0.7, so you know numerically moderate positive correlation. Now graphically, you mentioned that also, no? You mentioned that also. For example, probably this is what you will get, no? They should match. Okay, because sometimes the problem, class, is that in the graph you can make mistake in the graph if you don't have the basis, no, which is the number. Your number, in a way, your way of checking, because it's more accurate, because it has a number. It's a number. Here you can make mistake, no? That's why whatever the number tells you, follow it. Follow it. If the numbers tell you high, then graphically you may say strong. Okay, that's what I mean. If numerically the number tells you very high, still you can say graphically strong. Okay, something like that. That's what I mean. You match the two in your interpretation. Okay, class? So I think you understood what I mean. Okay, so now, the person-product moment correlation coefficient, or person correlation coefficient for short, is a measure of the strength. Now, there's the word linear. Linear relationship or linear association. That's another term, no? Linear association between the two variables. And this is denoted by small r or capital R. Basically, a person-product moment correlation attempts to draw a line of best fit through the data, no? To the data of the two variables, and the person correlation coefficient R indicates how far away all these data points are to this line of best fit. That is how well the data points fit this new model line of best fit. So those lines that you see here are what we call the lines of best fit, which we will discuss in part 2 with this equation. In fact, in part 2, that's what we will find, the M and the B, to get this equation, which is very important, because without this, you cannot predict the Y from X, right? Okay. The reason for prediction, class, is because the X values in your data are not complete. So what if you don't have the X values in your data and you want to find the Y? This is what you will use. Okay. But of course, it's not the exact. No, that's why we have to talk of the R and the R squared. By the way, in part 2, we will talk also of the R squared. The R squared, if R is the coefficient of correlation, the R squared is the coefficient of determination. So they are connected, because if you notice, R squared, so meaning to get the coefficient of determination, you square the coefficient of correlation. That's why they are really related. We will use that in part 2. regarding the how well your model is, no, in part 2. It will determine how well your model is. The R square determines how well your model is. The model is this one, no? How well the X values predict the Y values. It's related to the R square, okay, which is connected to this part 1, R correlation. Okay, so I'm just telling you the connection, the bridge the bridge to the next part, and that is the R squared. Okay, class. So and also you will see this if the numerically you have very high or high positive correlation, you know that the points, no, I'm sorry, why am I here? You know that the points are what? Very near to the line, no? Because strong, right? Very near. Some of the points overlap, no? May overlap. Okay, that's why, yeah, that number, that's what it tells you, no? That number there, no, tells you that also graphically. In a way, that's one way to interpret also when you say strong positive correlation. You can say that in your interpretation of your data, no? In your future research, that your data, these points are near to the line. Okay, so this one far already, no, that's why weak. So expect that numerically your value will be for the weak. Okay, what is that? For this one, the low positive, no, the weak, low positive correlation. So they should match, no? They should match. But if I'm sorry. This two pala, this two. Oh wait, I'm sorry. No, I'm correct. This is one because this one is for the no correlation, right? The negligible. This one is for the no correlation at all. Okay? Whether it's whether it's negative or positive, now we can just say no correlation or no negligible. But numerically, if we get something like this, numerically low positive or low negative. However, graphically, you may say it is weak. So meaning the points are far, no overlapping. In a way, you can say no overlapping. For this one, neither far, neither near. But you may have some overlapping here also, no? Some overlapping. Okay, so moderate. But numerically, you will get this value, no? Moderate, 0.5 to 0.7. Or negative, if it's negative, negative 0.7 to negative 0.5. Okay, class? Yeah. So we can have this example. Let's have an example to apply this formula. Okay, and to concretize what we have discussed so far, no? To concretize it. So this example on the age and glucose level. If you notice, class, there's already a variable, no? The X, and then glucose level, the Y. But again, in this context, it doesn't matter now which one is your independent, dependent. But since, because of course, if this is your study, for example, this is your study, and there's a question already, there's a hypothesis, you know already that you have already an idea that you may use this in part 2. That's why here in part 1, you may already decide which one is your dependent, independent. Okay, so the assumption is like that. That's why here we assume age as the independent and the Y, the glucose level. Okay. Anyway, as I mentioned, whether we assume that or not, it will not affect the correlation, the value of correlation. We can have this as your Y, you can have this as your X. It will not affect the value, but it will affect the what do you call this? The linear regression, the part 2. Okay, it will affect. The result for part 2 will be different now. If you make this X and then Y, is different from the result of if you make this Y and then this X. It will affect. Okay, so if you will use, actually, you will really use this, not this correlation in part 2. But the thing here is, if you will proceed to part 2, no? So I think in general, just identify your X and your Y. Usually in your study, in your research, since you have a question already, you can identify the X and the Y because your question in your study, in your research, future research, will determine what you want to find out. If you want to find the cause and effect, because class, once you in part 2, there's already a cause and effect relationship now. If you identify it as independent, dependent, meaning it's this like the effect, this is the cause, no? In that context of part 2. Okay. So now, so what we'll do first class is the scatter plot. So I'll show you. I will not do this manually to you. Okay. So instead, we'll use the Excel file to show the scatter plot of this, and that should be the case actually. No, I know you already experienced plotting in high school, no, plotting points, no. So I don't think you need more practice on that. Plotting points, the X, Y, right? So no need, no. Because that's enough experience for you to appreciate that we can make the scatter plot of this using the Excel file. And Excel file is very useful, and other software. We have a big data. This one is just very, very small data. We only have 6, no? 6, the sample, probably the sample size is just 6, very small. To illustrate the idea only, you know, that's the purpose of this. Okay, let me show you now that Excel file. But it's this one, the age and the glucose. But let me remove this because I use this in the other class now. Age and glucose, but let's just focus on this, the scatter plot. But here you already have, right, a scatter plot. But I'll show you how to get this, given this, this data set. Okay. Same data set as that in the PowerPoint. So what you do, class, is go to this, insert. Wait, where is this? I'm already here. Insert, and then go to this one. This one is the scatter plot, not this one. Okay, but before you click this class, you highlight first, including the column names, no? So this one, so go to this one, and then highlight here, up to here, no? So there. Okay, so that you can get this, no? Okay, let me show you. So let's go to this again. Then click. So there, did you see that? It's the same thing, no? It's just this one you can edit, not the title. Isn't it the same thing as this one? It's just the same thing, no? Wait, how do I move this? I can't move it. Let me move it there. No? Okay. So now, class, graphically, what can you say about your about the correlation of your data? Is it, you know, you have an idea already, it's kind of positive, right? The direction positive. In fact, class, below the orange there, if you connect those orange points, you get the line of best fit, no? The line of best fit. Okay, we can use this as a comparison. This one. This thing here. So based on this one, what can you say about your, and how the points? Is it strong? You know already it's positive, no? Is it strong? A positive correlation, moderate positive correlation, or weak? If you look at this, it's not strong, right? Because there are points like far, but there are some points that kind of overlapping. That's why we can say it's moderate, no? And not weak because there are some overlapping, no? If it's not full, but it's partially, right? So moderate. But again, that's our guess because it's kind of, it's a graph. Better if we have the value, no? So let's find out the value. Okay, class? To check if our guess is correct. Is it really moderate? No? So that's where we will use the computational part. But later I'll show you the using Excel. Probably you saw it already, right? The value there. But okay, let me go back to the PowerPoint and go back there again. Okay, so to use the formula, this is what the columns that you need are this. The xy, the x squared, the y squared. Because later you'll get the sum of all of this and then input the values into the formula. Okay, so xy, so meaning 43 times 99, so there, for 21 times 65, okay, and so on and so forth. Okay, so just imagine if you do it manually, no? That's why it's enough to have experience once, no? Once, twice, it's up to you. And then, but definitely in your research, you don't do this anymore, no? Or and more in your work, no? Or you don't do this anymore. Use the software. Okay. So next is the x squared. So just square the x. 43 times 43, this one. 21 times 21, this one, and so on and so forth. And the y squared. Okay. For 99 times 99 is this. 65 times 65 is this, and so on and so forth. And then add all of this. Because in the formula, you have summation x. Summation x means add all of the sum of all this. Summation y, the sum of all of this. So you have summation xy also in the formula, right? Sum. So add all of this, add all of this, add all of this. That's why all of this you will substitute into the formula and you will get this answer now, 0.529809. So just substitute and you will get using calculator. No? Now, based on the table, it's what? It's moderate. So our guess is correct graphically. No? So they should match. No? They match. Okay. But if your guess is wrong graphically, then in your research, research, you have to correct it. No? You don't put the wrong one there. No? You have to correct it. So that's why we need this, no, the R. Okay, so indeed it's correct. Moderate positive correlation. Now, how do you find this in the Excel? Okay, let me show you. So actually you have the answer here, no? The same, right? The same. How do you get this? Okay, let me double click so that you will see. So there, that's how you do it. Okay, they're highlighted because this is what we want. But the question is, where do you find this? The meaning correlation. Okay, this is okay. I'll go to this one, the empty cell here, empty cell. Then I will put equal. Yeah, that's all. Always you have to do that, equal, and then go to insert again, or the formula. I mean the formulas, and then insert function. In the insert function, you will find Corel. This one, because I already used in the other class, that's why it's here. But if it's not here, in the most recently used, you have to find here in the under all. It's alphabetized. That's why you just have to look for it. Alphabetized. So Corel. Then click that, Corel, insert function. And then you notice here, class, array1, array2, but it doesn't say x, y. But later, class, in the discussion of linear regression, it will be mentioned the x and the y, because there it matters. But here, class, it doesn't matter. But again, since we will use this in part 2, that's why we already decide this is our x, this is our y. So, so it doesn't matter where you put the x here. You can put the x here or the x here. It doesn't matter. Okay, but we just have to make clear already in part 1 that this is our dependent, this is our independent. But when you input here, it doesn't matter. But in part 2, it matters. Okay, because there is like x here, then y. So it matters. I think the first one is y. So that's why you have to put this. The next one is x. That's why you have to put this in part 2. For this one, I'll make y the x. Okay? Anyway, it doesn't matter. It will not affect the value. You will get the same answer. No? Okay, how do you put it here? You will not write all of this here. No. It's impractical, no? Especially if you have a lot of values here. No? You will not do that. Instead, you can decide this way. No? You highlight. Click this. So you notice it's already here, A2. And then drag it. No? Drag it. But in my laptop, there's a way for me to do it without dragging it. So I'll just point here and then press shift. So there, it's already, all of this will be considered there. But you notice, class, A2 colon A7. So another way of putting this is writing instead of highlighting. So I'll do it on the second array. So there. So instead of highlighting, I'll use the writing. No? So since I want these values from B2, because column B, so B2 colon. Colon means it's like the dragging, you have to drag it up to here. So B7. So there, so you notice also highlighted now. And then I can just do done. So you notice, you can write here, class. You can also write here. It doesn't matter. You can write it here, or you can write it here, or you can drag it here, and then it will reflect there. Okay, it doesn't really matter. So then done. Actually, here you can see the answer already right here. The same 0.52. But if you click done, it will be reflected here. So same answer. Okay, so that's how you do for the R. Okay, class. So I think that's it for the first part, if I'm not mistaken. Yeah. So this is now the part 2. Okay, class, the simple linear regression. Okay, if we have time, we can go back to this now. We will go back to this if we have time. Okay. Otherwise, you can do it as an activity. Apply what we learn here. Apply it here. Meaning, we'll get the y. Where is that? Because in part 2, our goal is to get the y is equal to mx plus b, na? Mx plus b. That's our goal. So we'll go back to this if we have time. Otherwise, it's your activity. Find this, no? After learning part 2. Because in that class, to do part 2, you have to do part 1. Okay, you have to do part 1 to do part 2. Because as I mentioned, in part 2, we will use the coefficient of determination denoted as r squared. Okay, that tells you the percent of accuracy of the prediction of your model in the form of linear function y equals mx plus v. Okay, that's why you need to find the r, right? You need to find the r so that you can get the coefficient of determination to tell you the how well the x values predict the y values. But it's possible that you won't go to part 2, you only do part 1, right? Part 1. And also part 1 will tell you if there's a need to go to part 2, depending on the study. Because as I mentioned, the r squared has to do with the percent of accuracy of your prediction. So there are some studies, they want like above 50%. Okay, 50%. So that you can say that the model is good. Other studies want 90%. So the r squared will tell you that, no? Okay, so let's proceed how to get this and manually and using Excel, no? Using Excel. But again, there are other softwares class. Just I mentioned, no? SPSS, but that one you have to buy it. It's licensed. And then there's a free download, the PSPP. I don't know if you downloaded it already. You can also use that to find the correlation, but you have to explore that. No, that's a software, so you have to explore that. It's like more complete, no, more advanced than the Excel, no. But in the next lesson, we'll use there we will use now because it's part of the lesson that we use that. We use that software which is the XL Stat, no, XL Stat. But their class we will use it for that lesson, not for this one. But if we have time, probably we can relate it also, no. To get this correlation and this linear regression in that software. We can also, if we have time. But again, that software is to be used for that lesson only. No? But if we have time, we can use that software to get the correlation or this simple linear regression. So for this one class, we'll use Excel file again. That's the free one. Without don't have to pay for it, no? Just to illustrate the point that you can get the y equals mx plus v without doing it manually. But of course, the focus in part 2 is manually for you to be able to appreciate the technology, and that is the software. Okay, to get this equation, this line of best fit. Okay, class. So let's dive in to the second part, which is the simple linear regression. Okay, so what is simple linear regression? Simple linear regression analysis is a technique that is used to model the dependency. Now, there's a mention of dependency, not anymore relationship. Unlike in part 1, relationship, no? It's used to model the dependency of one dependent variable upon one independent variable. So you see here now the cause and effect, not just association or relationship. But of course, if you have this, there's a relationship. No? There is association, and the association is that cause and effect. Okay. Whereas in correlation, it's kind of general, just the relationship, and the relationship is that we talk about there is the linear. No? Okay, this relationship between these two variables explained by an equation, and that's the one I showed to you in part 1, which is the y equals mx plus b. Regression and correlation are actually fundamentally the same statistical procedure. The difference is essentially in what your purpose is, what you're trying to find out. In correlation, we're generally looking at the strength of a relationship or a strength of a linear relationship between two variables x and y. Where in regression, we're specifically concerned with how well we can predict y from x, right? Because this is part of inferential statistics. We use it for prediction. The model, we use it for prediction. So here, class, when you talk of simple linear regression or simple regression, only one independent variable is involved. In fact, only one dependent variable also, okay? Because there's what you call multiple regression, which we'll not discuss in detail, but somehow related to the next lesson, multiple regression. For multiple regression, you have more than one independent variable. But again, we will not discuss it in detail. No, I just want to mention to you because it's kind of related to the next lesson, the multiple regression. So this one is simple regression. We can also call it linear regression or simple linear regression. And then the relationship between x and y or y and x is described by a linear function. Changes in y are assumed to be caused by changes in x. So that's why there's a cause and effect. Okay, class. So now, this identification of or assignment of dependent, no, dependent variable, independent variable, very important. Now, as discussed here, no, it's discussed in education research. For example, in education research, examples of the use of regression in education research include defining and identifying underachievement or specific learning difficulties. For example, by determining whether a pupil's reading attainment, so that's why, is at the level that would be predicted from an IQ test X. So that's your X. So always, class, when you predict, you want to predict the Y, huh? Not the X. You only use the X to predict the Y. Okay. So another example would be screening tests, perhaps to identify children at risk of later educational failure so that they may receive additional support or be involved in early intervention schemes. So in regression, it's convenient to define X as explanatory or predictor or independent variable. This is important, class, huh? Because in the next lesson, we'll use most of the time explanatory, but you're more familiar with independent. No? So if it's this mentioned, you know already it's independent. Huh? Okay, and Y as the outcome or dependent variable. Now, in the next lesson, this is more called response, no response variable. But again, yeah, it's still mentioned the dependent, but usually it's mentioned there as the response. It's the same thing as dependent anyway. We're concerned with determining how well X can predict Y. So that's what is important now in linear regression, which is connected to the R squared, the coefficient of determination. How well X can predict Y, or how good your model is. And the model here is an equation, a linear function in particular. Because in the next lesson, we'll talk of another function that models the dependent variable, no? A different function, not linear function anymore. Only for this one, the linear regression. It's important to know which variable is the outcome, or the response, or the dependent, and which is the explanatory variable, or the independent variable, or the predictor. This may sound obvious, but in education research, it's not always clear. For example, does greater interest in reading predict better reading skills? So meaning, it's predict better reading, so this is the Y. Does the X predict the Y? Okay, in particular, does greater interest in reading predict better reading skills? Possibly, because this is also possible. But it may be that having better reading skills encourages greater interest in reading. So meaning this now will become your X. So instead of Y, the X encourages the Y. So you notice it depends. Now, better reading skills can be X or Y depending on the. Actually, it will help. The question will help you. The question of your research, right? This is in the context of what? This is in the context of scientific the research in a way, no? Or that similar to the steps of scientific method. You have a question, hypothesis, methodology. So that it will help you to identify your X and Y. Go back to the question, to the question of your research, no? Okay, and then you'll be able to know the X and Y. Education research is littered with such chicken and egg arguments. Make sure that you know what your hypothesis about the relationship is, and when you perform a regression analysis, and it's fundamental to your interpretation. Okay, it will affect. Excuse me, because, for example, you apply regression analysis not to your data, wherein in your data you consider this as your X, the reading skills, no, and your Y, your interest, no. Excuse me, but the result will be different if you make this Y and the other one X. Will have different results, no. That's why the solution there, excuse me, the solution there is go back to the question. Go back to the question of your study. Okay, class. So now, if you will go to this one, there's like a focus on education research. So don't be misled, no, because again, this is very useful in business, no. This topic, the statistics in general, no, very useful in business. So it's just that in this lesson, our examples are focused on the education. Okay, but again, this is very useful, no, to business. So it has business applications. Okay, class. So let's proceed. Now this one is just to show you how we can make a prediction using a scatter plot. So this is a scatter plot. So this one only shows you the Like if you have the line of best fit, for example, this is the line of best fit, na? There's an error, no, because they don't overlap the actual points. So this is like your actual points, and then this is the corresponding in your line of best fit, the corresponding predicted point. So there's a difference. So our goal, class, is to minimize this error, this difference, to minimize. So come up with your what? The line of best fit. And there's what you call, that's this method of least squares method, which we will not discuss here now, but that's the method applied here to minimize these squares, no? To minimize this this difference. Okay, apply the least squares method, and that least squares method is applied to get this, the formula for getting the m and the b in our model y equals mx plus b. Okay, to find that, and other assumptions. The other assumptions I will discuss later, but before that, let's go to this one. So this one, yeah, still about that, no? Regression line, no? You can also call this the regression line, no? But if you don't have the method, you can you can approximate estimate, no? But of course, since it's estimation, it's not accurate. That's why it's better to have a method to find that line, no? The line of best fit, no? Okay, so this one is like explaining, no, partially, no, how to the method, this method of the least squares method, no? Minimize differences between the actual y values and the y value. Okay, and these differences are squared so that the negative signs are removed. Hence the term sum of squares, which you may have come across before, no? So okay, this one only talks about the method, no? Okay, but again, we will not do it in detail. Okay, that's the assumption, to get this line of best fit. And to get this line of best fit, what we need really is the formula for m and b. If we will we'll do it manually, no? But if we will do it using software, no need for the formula, right? No need. But for the software class, this is considered, no, the formula, no? That's what being applied in the software, the formula, no? So that on our part, we just have to do the clicking, no? But the computation will be done by the software. But now, class, so that you will appreciate the software or that technology, it's good that you experience the computation, and that's what we'll do in the following slides, no? The computational part. Initially, but later in your research or in the work setting, you don't do the manually, just apply the software. Okay. So now this is just an example. For example, this is the m that you got from the formula that I will show to you later, the formula for m, and the b and this one. But of course, in the software, it will just give this to you, this two. Okay, without you computing for it. Okay, this one refers to the sample, no? Like we base it from the sample. But if you base it from the population, you can use this. The alpha, the same meaning. The alpha is just the b, no? The beta is like the m. It's just that this one is what? In population context. Because remember, if we're using the population as your data, then use the Greek letters for your parameters, no? Parameters. Okay, the alpha, beta. But usually, class, this is what we use, no? Not this one. Rarely that we use this, no? This one. Okay, and besides, this formula is for the sample, no? The formula that we will use later for the sample. Now, again, explore on this part now. If your data is population, then explore on the formula of alpha and beta. Okay, since our examples just deal with sample, we'll use this. Okay, just explaining the error, class, now this part. Okay, that's error, and also that part of prediction. No? For example, if the x value is 3.5, so we see that an x value of 3.5 predicts about y value of about 7. Meaning, just substitute here, no, and it's about 7, the value, the y value. So this is the idea of the class, no? The prediction. Because in your data, you don't have 3.5 now. You have 2, you have 1, you have 3, you have 4, you have 5, you have 6. But you don't have 3.5. So now that's the use of the model, no? To get the y value, the corresponding y value. Okay, so this one just talks about the error, no? That there is an error. No? Okay, but you notice the higher the correlation, the smaller these errors. That's why you notice it's related to the part 1. And more related to r squared. Related to r, but more related to r squared. It's mentioned here. The higher the correlation, the smaller this error. And we want small error, no? We assume class, if it's the line of best fit, that's why line of best fit, no? It's not line of good fit or better fit, but the line of best fit, meaning that's already the minimum error that we can get, no? It's already computed because of the least square method and the assumptions that we will discuss later, or probably the next slide we'll see. Okay. So again, yeah, this is what we will use instead of this, because you can use this, but we will use this instead because you're most familiar with this. Okay. So, but it's okay also if you use this, but in the formula, I just refer it to M, the B, the M, but the B here, the A. Okay, so anyway, so these are the assumptions I'm talking about now. Aside from the least square method, these assumptions are important, no? To arrive at the formula of M and B. Okay, important. So what are these assumptions? Linearity, the mean of each error is 0. Independence of error terms, the errors are independent of each other. Normality of error terms, the error of each variable is normally distributed. Homoscedasticity, the variance of the error for the value of each variable is the same. I will not discuss this in detail except this one. This is connected to what we discussed last time, the normal distribution. So here, class, we want our y values, the y values, na, follow the normal distribution. Meaning, for example, in part 1, we talk about what? We talk about the age and the glucose levels. The age is the independent variable. The y is our what? Dependent variable. So that y, or that dependent variable, we want it to follow the normal distribution. Normal distribution. That's the assumption, ano? So that we can compute for the M and the B. Okay, class? So these are the formulas for the M and B. And this is for the B, no? The M and then the B. Okay, so you can use this or split into 2 so that you can use the mean. Right? This is just the mean, no? And this is the mean. Okay, so indeed, what is used here is M, no? Not the other formula. The y equals mx. Y equals mx plus b. Okay, class. Now these are like the steps. If you want to do it manually, no, by hand, I remove this because we just need the x. No? Also, I just removed which you will not use. Okay, you'll understand this better if you apply it in an example. So let's have an example. So this is the second example, no? The number of chimpanzees, so that's our independent variable. Percent successful hands, that's our dependent variable. So our goal here, class, is to come up with a model, right? The model in the form of y equals mx plus b, so that the x can predict the y. That's what we want to do, right? To predict the y based on the values of x. For example, we don't have here 9, no? So what is the percent successful hand if it's 9, 10, 11, like that? Okay, that's the reason, because we have limited data. Okay, and the accuracy of that model depends on the R squared. That's also important. And again, it depends on the study, no? Regarding that, not the percent of accuracy. Okay, first, class, as I mentioned, this is related to part 1, because before you get before you proceed to regression analysis, you have to do part 1. What is that part 1? Scatter plot. Get the scatter plot first. So let me show you the Excel file again regarding the scatter plot, and then let's describe the correlation of these two graphically and numerically, because we will also use Excel file to get the R. Not anymore manually, no, because we already have Excel file. So if you know other software, you can explore that software that you know, like if you already downloaded the PSPP, you can find the there how to find the R. Okay, and if we have time in the next lesson, if we have time, we will try also to find the part there in the Excel stat where we can compute for the R, and also the scatter plot, and also the linear regression. But again, after doing the lesson, okay, if we have time. Otherwise, in the future lessons, if we have remaining sessions left, okay. So let's proceed to the Excel to look at the scatter plot. Okay, so let me go to this, the chimpanzees. So their class. So this is your X. So you notice, it's nice scatter plot, no, class. So here you can already see now it's like the strong, right? And also the correlation, you know, already it's positive, no? Even without looking at the orange, no? But by looking at the orange, this line of best fit, there is really overlapping, no? So you already know it's graphically, it's strong positive correlation. And numerically, look at the number. Look at the number, 0.96 na. 0.96. So they match na, graphically and numerically. Now we're ready to get the, okay, later I'll show you the Excel na for the finding the M and the B. Okay, so let's do first the manual. So with that class, with that value of R, though it's not yet complete, no? Okay, let me show you the R squared also. The R squared is also high. Look at the R squared. Isn't it also high? It's lower than 0.96, but it's high, 0.92. All you have to do is square this. So this one tells you the accuracy. So meaning 92 or 93% the accuracy of your model, the prediction. Meaning, if you want to predict for the 9, that model will give you 93% accuracy for the X value. So with that value of R, with that strong positive correlation graphically and very high, no? This is very high, no? Very high positive correlation. And this one, the high coefficient of determination, tells you already that it's good to proceed to part 2. And also depending on your study, no? Depending. Because sometimes even if you get here, R squared is 0.5, 0.55, but the study allows you, then you can proceed to part 2, meaning you can find that equation. In fact, you already have here, no? This one, no? This is the model. But we got this here, no? Excel file, using the Excel file. But I'll show you how to get this manually, no? Okay, let me go back there. We will proceed to part 2 because it's high, no? 92. And also, again, it depends. You also have, it depends on your study, no? Because even though it's not high, it's 0.55, as I mentioned repeatedly already, you may proceed, no? Depending on the study. Okay, so let's do that. Let's go to the manual. Yeah, these are, so I erased this because we don't need this in the formula, no? We don't need it in the formula. So just this one, so just the same thing, no? We add all of this so that we can substitute into the formula. To the formula there, no? The M and the B. And indeed, we get the same answer as that in the Excel, no? You notice? Same answer. Okay, class. So for now, for the Excel file, I think you know what to do already, right? Because I already showed it to you for R. So same thing. So this one, the slope. So this is like what you will write there, no? Slope. But where will you get the slope? Again, in the insert function. Okay, I will not do it in detail anymore, but I'll just, okay, let me put here. So same thing, just like what you did for R. So put the equal, and then, okay, I'll do it for this one, equals, and then go to insert function. You already, formulas, and then insert function, and then you will see here slope. But since I use this in the other class, that's why it's here. But you can go here, no? Alphabetize. Okay, alphabetically arrange. So click slope. So then insert function. Now you notice there's y and x. So there, that's important. You have to put the x here, the y here. So my y is this, no? Not this, no? Because if you put this, it will have different result, no? So you have to put this. Unlike in correlation, it doesn't matter. That's why in the array, you don't. It's not mentioned. It's not indicated the y and the x. But here in the array, it's indicated the y and the x. This is our y. So again, same style as that for R. You can highlight or write. Okay, so this one, and then that's why I have B2 now, B2, and then drag, or in my laptop, I don't need to drag. I just have to click this, and then there. So B9. So okay, and here you can write. No, it's up to you. But I just drag it. I'll just click here, and then there. Okay, and then done. Actually, you have the answer already here, no? 5 point, same as this, no? Same, should be, because the same data. So done. So there you go. So same answer. So similarly for intercept, no? Intercept. So where do you get the intercept? Again, in that list, no? In the insert function again, no? So let me remove this. So there, here also. So there is the intercept. Okay, so it's not here. I think I did not use it in the previous class. It's here. Find it here. Intercept. No. Okay. Same idea. Okay. So I guess this one also important. No. The x and the y. Yeah. Where's the intercept? So there, intercept. But again, you have to put the equal here first. No. Equals. No. Like that. No. You have to put that. Let me try. So intercept and then there. Okay, so it will not, there's a problem. You have to put the equal here first, no? But you notice for the intercept, also important, the y and the x. Okay, so that's, you can do this by yourself. You know what to do now. Okay, class, so there, once you have that, you can just put this. Whereas, class, the other software will give you the equation. This one, for this Excel, you have to compute for the M and B, and you'll be the one to write this. But there is a software like that one, the Excel Stat, or the SPSS, or the PSPP, or the R. There's also a software R wherein it will give you a lot of data, no? Not only this, no? A lot of data, the graph, so many data. Even if you don't ask for it, it will give you. It will give you, no? Okay. This one, it will be written for you, no? So I hope we have time for that next meeting, no? Next lesson. Or if not, in the future session, no? If you have remaining time. Okay, remaining time. Okay, class. So I think that's clear now. So meaning, class, the graph of this is the orange, no? If you connect the orange by a line, that's the equation there is this. The graph of this is that orange line. Okay, that's the idea. Now you can predict your y values from the x. And the accuracy is 92%. The accuracy that the y is correct. The y value that you will get is correct, is 92 or 93%. Okay, class. So I think that's clear now, the use of this linear regression. Okay, but we have another example to emphasize it, to make it clearer now. But I know it's clear already. No? Okay, so with the Excel file and with the computation, I think that's very clear. But again, let's have another example. So this one is the grade and the words on essay. So the grade here is our x, the words on essay is our y. So that means we want to have a model predicting the words on essay based on the grade. For example, we want to know how many words on essay that a student can write if his or her grade is not here. For example, 98. There's no 98 here. So that's the use of that model. Okay, but of course, it's prediction, so there is a % of accuracy of the prediction based on the R squared. Okay, but again, even if it's kind of low, like for example, 0.55, 0.57, it for some studies it's acceptable. It's acceptable. Okay, but I don't think the below 0.5, no, the below 0.5 is not acceptable anymore, no. Because what's the use of that model if it will not predict your y value accurately, right? Because remember, we use the model to make a decision. So in a business context, to make a business decision, if your model is not good, your decision will not be good also, right? And if it's a business, it will affect the profit, right? The profit, and probably your business will not become successful, no, if your model is not good. Okay, so that's the idea here, class. Now that's the idea. So now let's do the what's supposed to be done. If you're given the data set, this data set, the first step is scatter plot. After the scatter plot, the R, and then the R squared. The R squared will tell you whether to proceed to part 1, part 2, to find that line of best fit, depending on the study. Okay, depending on your study. Okay, so let's get the what do you call this? The scatter plot. So the scatter plot of this is this one. But if you look at it, it doesn't look nice, nah? The scatter plot of this one, the grade words on essay. But better if you have that idea of the line of best fit, nah? If you look at the line of best fit, you can describe the correlation of your data graphically, nah? So there's some overlapping. Somehow. You may say it's kind of not very high, but high, right? Or since it's high, then you may say it's strong, somehow strong positive correlation. And you can see that in the R, no? Look at the R. The R is 0.92. 0.92. Is it very high if it's ano? I think it's very high also, right? Based on the table. Because on the table, 0.90, right? Is it? Okay, I forgot about it. So let's just go there. So yeah, so you have to go back now. Yeah, it's still in part 1, right? Okay, yeah, it's still very high pala. So 0.7 to 0.9, that's the high positive. So the number tells you it's very high, no? Even though graphically it doesn't seem to be very high, but graphically it's strong, no? Based on the ano. Okay, let's go back. Where are we? Okay, there. So the words and assay, that's the computational part. But before I go there, let me this one will tell you that it's graphically it's strong. But if you just base it here, it's kind of doubtful. Okay, but again, you have to match the number. So even though graphically you have to follow the number. The number tells you very high, so that means strong. Okay. Now, if you get the R squared, it's kind of lower, but still kind of high also, 85. So again, it depends on the study, no? So here we can proceed, and this is our model. Okay. To get this, you know already, right? How to get the M using Excel, no? Using Excel. Okay. So now, if you have grades, as I mentioned, no, you can use this, no, and substitute 98. Substitute here, you can get the Y. And that's your predicted value for the word on essay. Because that's what we want to predict, no? The Y, the dependent variable. Okay, class? So in the next lesson, class, we'll talk of another regression to predict the dependent, still the dependent. When we predict, always the dependent, but we'll use another regression, another type of regression, and another function, not anymore linear. Okay, anyway, let's just finish this manually. Let's do the manual computation of this. Let's go back to the so that you can appreciate the technology, not that software. Okay, again, the same thing in the second example. Just get that, no? Okay, compute for it, and then yeah. But you notice here, class, they're different because the right one really is this one, 144. 145.27. If you will notice now in the Excel, it's really this, the correct one. However, this is the right one if you base it on the rounded off. That's why there's a round off error. No, that's the problem with manual. No, so of course you have to follow this. No, I just erase it. No, just to emphasize the point that this is a round off error. No, but for the computation, this is correct. Okay, so you may use this or this, but again, better this one because you're expected to use the Excel. No. This one is just to appreciate the Excel, the use of Excel. Okay, so so there, no. So indeed, we have the that's the one we have. No, it's just that here put in words, no, but actually that's the one in the Excel, no. Except this, we have to change this to this one, no, to get the more a better model, no. So replace this by this. Okay, the exam grade is actually the X now. Okay, so that's the one in the Excel file. So now, as I mentioned, this is the coefficient of determination. Now, the coefficient of determination explains 85%, okay, 85% of the variation in the number of words on the essay. So meaning the coefficient of determination determines the variation in the values of your Y. Remember, words on essay is in general the values of Y. In other words, exam grades, that's the X, strongly predict how many words a student will write in their essay. So the X values strongly predict the Y values. That's what that's what the R squared, the coefficient of determination, tells you. But again, it depends on the study because even if R squared is 0.60, if that study allows it, then you can use it in your research. Okay, for the model, for your model. Okay, for the model of the Y value or dependent variable. Okay, class. So we still have time. So I think this is the last one, but I'll show you the online. There's an online way to not only the computational, not only the Excel, but also the online. Let me show you that. Yeah, this one. Let me show you the website. Easy calculation. Easy calculation. So meaning class, for example, this one, the line of best fit. If you want to get that, you can put here the X value, The name of X value. Yeah, I think I'll do the glucose. Remember I told you the glucose level. So let's say the X here is the age, not the age. And then here is the glucose level. Glucose level. And the value here, the value of the X value, what are the X values? You remember? Okay, let's go back there. So we have to go back there. Unless I have a copy here. Yeah, yeah, the Excel. We can go to the Excel. That Excel. Because there, you notice the R here. It's moderate only, na. So not high, not very high, moderate. And then if you get the R squared, very low, eh. Did you get that? Very low, 0.28. So actually, for the purpose of discussion, let's get it. But actually, it's not a good model because of the 0.28. You understand me? It's 0.5, eh? Below 0.5. So meaning this one is a bad model, no? But just for the purpose of discussion, let's consider it, no? Let's consider it. But in your actual research or in the work setting, don't proceed to this one, no? Don't use this as a model. Of course, you can push this, but it's not accurate. The percent of accuracy is only 28%. That's why instead of the R, but the R squared is already the R, as I mentioned, but really your basis of decision is the R squared, not the R. The R squared. It's very low, eh? Okay, did you see that? Okay, let me put these values just to show you my example. 43, 21. Okay, how do I do this? 43. So let's put that. 43. How do I put this? 21, and then add more. 43, 21, 25. 42, 57, right? 42, 57, 57, 59. 59. And then the corresponding Y value, you have 99.65, na? 99.65. And then what else do you have? 99.65. 79.75. 79.75. And then 87.81. Right? 87.81. Okay? So is it correct? 43.99, 21.65, 25.79, 42.75, 57.87, 59.81. Now generate chart. Generate. So here you don't have a result, right? But the equation used is this, no? You notice the trend line equation is the line of best fit. The A plus BX or the Y equals MX plus B. No, it's the same thing. And then this is the formula. Remember the slope, we have the formula. So in other words, whether it's software or online, same formula is used. It's just it's programmed already. Whereas in the manual, well, you'll be the one to do this. Okay, let's generate. No? So there, did you see? Oh, there. Oh. Did you see that? So this is the this is your remove the line here. This is the scatter plot. Actually, we call it the scatter line. But removing the line, we call it scatter plot. Now, this blue line is the line of best fit. The line of best fit. Okay, now you can do the same thing for practice now for the other two examples. Okay, class? Now, actually, this is not the only website, no? That's where you can apply. There's another website here, which we will use this next class. But here, class, you're given data already, no? Not our data, but other data. Okay, the website is this one, DataTub. You can Google it, datatub.net, no? And then you will get the same thing, no? So here, class, linear regression, no? So meaning I want to get the linear regression of the salary and the age. So there's the result. Okay, the result is here. But here, class, you have to get the equation pa. You have to get the equation. The equation is this, no? It has to do with this. Y is equal to 43.3x plus 623.58. It has to do with this, no? The model. This is the model, eh? So, but in the other, in the Excel stat that I will show to you next lesson, the equation will be given, no? For this one, it's not, eh? You'll be the one, you should know how to write the equation, no? You should know how to write. Yeah, you should know. But here, this is how you do it. No? In this model, no? You have the model. So y is equal to 43.3 plus 623.58, the h, the constant. This one corresponds to the slope, the m. But you notice, class, you have here the r already, no? The r squared. So 46, not good also. Below 50%, no? Okay, so I think I can end there, but I want to discuss more. Even to say you can try any of this, no? Dependent, your independent variable, no? You can choose here the gender, salary, no? But of course, you can only choose, because for this one class, the x and y numbers only. So choose the one with numbers like salary, age, no? Next lesson, it's possible to have qualitative data as your y variable, as your dependent or independent, no? Qualitative data, and that will be for next lesson. I think I can end there, class. I think you understand it well. Okay, class, so these are the references. So that ends the lesson for this week. Thank you very much for attending. Bye for now.